Welcome back to The Explainer. Okay, we're jumping right in today because we are tackling a seriously fascinating piece of the AI puzzle. It's called defuzzification. Now, I know, it sounds like a made-up word from a sci-fi movie, right? But it's actually the absolutely crucial final step in any fuzzy logic system. If you've ever found yourself wondering how your smart appliances actually make decisions, well, this is the hidden mathematical magic that makes the whole shebang possible. So think about this for a second. How does a machine that, thinks in fuzzy terms actually take a precise physical action? This is a massive engineering challenge. See, we design these fuzzy logic systems because we want machines to evaluate the world the way we do. We use imprecise gradient concepts like saying something is slightly warm or very fast or too close. But here's the catch, and it's a big one. A physical machine, like a motor or a valve, it literally has no idea what slightly warm means. It doesn't have a brain. It's just circuits. It absolutely requires strict, precise, binary instructions to do anything. So how do we bridge that gap? How do we get from human-like vague logic to the strict demands of physical hardware? Which brings us to Section 1, the Great Translator. What is defuzzification? Well, in a fuzzy system, after all your various if-then rules are evaluated, those fuzzy outcomes get combined. They get aggregated into this one unified, kind of messy shape. We call that an aggregated fuzzy set. But like we just talked about, you can't exactly send a messy shape to a motor. It just won't work. So defuzzification is this essential process of taking that aggregated, imprecise data and extracting just one single exact numerical value from it. We call that exact number a crisp output. Basically, it translates the fuzzy decision into a precise, actionable reality. Moving on to Section 2, the two directions, fuzzification versus defuzzification. Now, there's a really interesting imbalance of effort in these systems. At the very start, you have fuzzification. That takes precise data, say exactly 72 degrees Fahrenheit, and converts it into an imprecise category, like warm. And honestly, that's computationally super easy. It just relies on basic if-then rules. But look at the other side of the equation. Defuzzification does the exact opposite. It takes the vague and makes it mathematically exact. And that is some serious heavy lifting. Converting imprecise data back to precise data requires highly complex mathematics. It often relies on intense center of gravity calculations. So simply put, fuzzifying, super easy. Defuzzifying, really hard math. All right, Section 3. Grounding the theory, the hardware reality. So the big takeaway here is that we do all this complex math because physics literally demands it. A physical piece of hardware just cannot operate on a fuzzy command. Try sending a signal to a fan that says, hey, spin sort of fast. It's just going to sit there. It won't do a thing. Hardware operates on electricity, on physics, and on absolute metrics. It demands an exact control signal. It needs to know, give me exactly 5.2 volts or spin at exactly 1200 RPMs. Otherwise, it just can't function. And that is exactly where our crisp output goes. The source material outlines some very specific, tangible components that rely entirely on this translation. We're talking about stepper motors, which have to rotate in exact increments. We're talking about digital to analog or D to A converters and voltmeters. These components are literally the muscle of any automated system, from your smart washing machine all the way up to massive industrial robotics. And the crazy thing is, not a single one of them can flex a muscle without defuzzification providing that exact, crisp numerical signal. Let's hit Section 4, finding the crisp output. 4 diffuzzification methods. Now, as you might guess, there isn't just one single way to solve this math puzzle. Systems typically use one of 4 primary methods to extract that crisp output. First up, we have the centroid method, which is also known as the center of gravity method. Then there's the maximum membership principle, the weighted average method, and finally, the center of sums. And I want you to notice just how different these sound from fuzzification methods, which use stuff like neural networks or rank ordering. These 4 defuzzification methods, they are all about geometry and spatial mathematics. Let's actually look at the most popular of those methods in action, the centroid method. If you check out the overlapping triangular shapes here, these represent our fuzzy rules that have fired and been aggregated together into this one complex shaded geometric shape. What the centroid method does is calculate the exact center of gravity for this entire combined shape. Imagine, if you will, cutting that sheeted area out of a piece of cardboard, okay? Now try to balance it perfectly on the very tip of a pencil. that exact balancing point, that specific dot right there with the arrow pointing down, that is our defuzzified, crisp output. Here's another applied example of finding that estimate. Take a look at these three distinct membership functions. They kind of look like little mountain peaks, right, that have been combined on this graph. Now, the system doesn't just randomly pick one, it unifies all these shaded areas. By applying our defuzzification math, the system actually evaluates the total mass and the distribution of all that gray area, and then drops a line straight down to the horizontal axis at the bottom. That single specific point on the z-axis is our precise numerical estimate. It has literally taken three overlapping, vague maybes and transformed them into one definitive, do this right now. Which brings us to a really fascinating thought I want to leave you with today. We've just walked through some seriously complex mathematics, right? Translating fuzzy human concepts into the strict, crisp reality of stepper motors and control signals. But remember, this isn't just some abstract theory. This is happening all around you, literally right now. Just think about your own environment, your air conditioner adjusting its fan speed, your smart washing machine deciding exactly how much water to use based on the size of the load. They are constantly gathering vague data, evaluating it fuzzily, and then, in a fraction of a millisecond, defuzzying it to take a precise physical action. So how many crisp, defuzzified decisions is your own smart home making for you at this very moment? It is pretty incredible to think about the invisible mathematics shaping our everyday lives. Anyway, thank you so much for joining me for this explainer. Keep asking those questions, and I'll catch you on the next one.